Hey, everybody. We are into our next unit, and it's a very, very short one. Unit 2 only has three sections covered: Section 2.5, Section 2.6, and Section 2.7. So we've already done 2.5 and 2.6. 2.5 was about transformations, and 2.6 was about the operations on functions, including compositions and finding their domain. The homework for these two have been on my math lab for a few days now. We should have a quiz on that, so we can still get five quizzes for the semester, one quiz per test, really. And since we can only quiz or test on synchronous days, we can test on, or we can quiz on Tuesday. So then a week from today, Tuesday, September 29th, we'll have a quiz during class on these two sections. And then an exam on 2.5 through 2.7, 2 weeks from yesterday. So on Monday, October 5th, on 2.5 through 2.7. All the homework for these three sections are all on my math lab right now. So please finish them. I think 2.5 and 2.6 are due any day now. They've been out for about a week. 2.7 will be due the middle of next week. So this section is about inverses. And inverse functions, when two functions are inverses of each other, they undo each other. So for example, if a certain function maps 2 to -9, then the inverse function will take -9 and bring it back to 2, which is shown here. G of -9 will give you back to 2. And that occurs for every domain element. It'll just undo what was done. And operations have inverses. Like addition has an inverse. It's subtraction. Subtraction undoes whatever addition did. And multiplication and division are inverses of each other. So we're going to talk a lot about inverses. It's hopefully going to be a short video, but I do want to spend 2 days on this topic. We'll talk about how to find inverses algebraically and graphically, which should take up most of the time here. So first of all, let's think about it, just number sense wise, without any algebra. How would you find the inverse of 3x plus 2? So you need to find a function that completely undoes 3x plus 2. And it's very much like tying a shoe. So think about the process that you go through when you tie your shoe. You have your open shoe, and the first thing you do is you put it on your foot, and then you cross the laces and pull them tight. And then you do a loop and tie a knot, and then maybe you do a double knot. So that's four operations that you do. Well, hopefully there's a part of your brain that can undo all that. Otherwise, you'd have your shoe in your foot forever. So you have an inverse function to undo all that. And you have to undo it in a correct order. You have to start with the last thing you did. The last thing you did was a double knot. So to undo your shoe, the first thing you must do is undo that double knot. And then you must undo that loop knot that you made. And then you must undo the twisting of the strings and stretching it apart. And then finally, the last thing you do is take it off your foot. Remember, that was the first thing you did when you had to put on your shoe. So if you're a domain element, not too much is happening. Only two things. The first thing that's happening is you're being multiplied by 3, and then your 2 is being added to you. So to completely undo those two things, you have to do them in the correct order. The first thing you would do would be to undo the adding 2. So you would subtract 2, and then you would divide by 3, resulting in this function. So this is the inverse function of f of x. X minus 2 divided by 3 completely undoes everything that 3x plus 2 did. Let me show you what I mean by that. So here's the two tables of these functions with some ordered pairs. So f of 5 is 17, because 3 times 5 is 15 plus 2 is 17. Well, if you put 17 in this function, it'll get you back to 5. 17 minus 2 is is 15. And 15 divided by 3 is 5. You don't even have to really know the explicit definitions of these functions to answer some questions. For example, f of 1 is 5. If you look at this table, you can find 5 as a domain element, and it results in 1. So 1 gets mapped to 5, and then in the inverse, 5 gets mapped to 1. And if I were to put in 1/3 over here, imagine 1/3 of the domain. Well, 3 times a third is 1, and 1 plus 2 is 3. So if I put in a third into x, the result would be 3. Look over here. When 3 is the domain, 1/3 is the result. Well, how do we find the inverse? We kind of thought this one through and came up with the x minus 2 over 3. But some are so complicated that think we need a better way. We need a tool. And algebra is that tool. There's a way to do it. It's this recipe. We're going to let f of x equal y, and then you'll switch x and y. That's really the key part of this whole process, switching x and y, and then solve for y. If you end up getting a function, then ta-da, you have the inverse function of your first original function. So let's follow those steps. First, replace f of x with y. So this becomes y equals 3x plus 2. Then I switch x and y, so I get x equals 3y plus 2. Next step is to solve for y, so I'd have to subtract 2. And then to solve for y, I'd have to divide by 3. And this is a function. So I've got it. F inverse is x minus 2 over 3. Let's apply it to this. The radical x plus 5. So first, I'm going to switch fx with y. Then I need to solve for, I need to switch x and y. So I switch x and y. Now I need to solve for y, which involves subtracting 5 and also taking the square root. Well, back up here, what would you do first? If x got injected into this function first, would you take the square root first, or would you add 5 first? We would add 5 and then take the square root. So to undo all this, we undo it in the reverse order. First, we need to get rid of the square root. So we would square both sides and then subtract 5. And that is a function. So that is our inverse function. Now we have more to say about this, and we have to find the proper domain for these functions, because as it stands right now, we're in trouble. And here's what I mean. Let's talk about the inverse function. Oh, and by the way, the two functions, even though this one has like the inverse symbol, the -1, they're both inverses of each other. So f inverse will undo everything that f does, but also f will undo everything that f inverse does. It's this symbiotic relationship. So as it stands right now, f inverse of -4 is of course -4 squared minus 5, which is 16 minus 5, which is 11. So f inverse of -4 is 11. No debate. But then also realize that f inverse of 4 also gives you 11. No debate there. Now the problem is, if you take 11 and put it into f is supposed to undo what f inverse did. So my question is, where is f going to send 11? Is f going to send 11 to -4 or to +4? Because it has to get back to the original. It can't do both because it's a function. Functions take an x value and they send it to one y value only. So it can't be -4 and +4. Which one is it? Well, it ends up being +4, but we need to know in advance. And the way to know that is to what we call restrict the domain. We need to change the domain or adapt the domain so that both relationships are indeed functions and they are inverse functions of each other. And before we go on to that, we need to define one more thing. To verify if two functions are inverses of each other, you need to take their composition. But since composition is not commutative, you have to do it both ways, f of g and g of f, and the result has to be x. And really dwelling on this sentence will hopefully help us understand. What does that mean? F of g of x equals x. So first of all, think about the undoing aspect of it. When x goes into g produces something. That in turn goes into f, which produces x. But hold on a second, I started with x. So if the number x got manipulated by g, and then f in turn manipulated it back and gave you back x, what you started with. Same thing with g. Now here g will undo everything that f did. X will go into f changes it around, and then g changes it back into x. Here's like the cartoon version of that. Two functions, f and f inverse. It doesn't matter where I put these, okay, because they both behave the same way. They're both inverses of each other. So what goes in here? This is the f function. Well, only the domain of f can go into f. And then what comes out? The range of f. But since by taking the composition, the range of f has to equal the domain of my next function, which is f inverse. And f inverse will put out a range. But the whole point of an inverse is that the final end is what you began with. So the range of f inverse must equal the domain of f. So for example, f of negative 13, I meant to say. F of negative 13 is undefined because negative 13 can't even go into f. But f of 11 can. 11 can go into f. 11 plus 5 is 16, and the square root of 16 produces 4. So 11 will go in to f, and 4 would come out. Now, 4 is acting as like the range of f, but it's also simultaneously the domain of f inverse. So 4 goes into f inverse, and f inverse takes the input squared minus 5. So 4 squared minus 5, and I get 11. I get back 11. I get back exactly what I started with. For f inverse, f of negative 1 can't exist here. Not because negative 1 can't go into the parabola. Negative 1, you can square negative 1. But what's the problem with negative 1? This is the problem. The range of f has to be the domain of f inverse. And there's no way a square root function will produce negative 1. When you take the square root of x plus 5, the result is always positive or 0. It'll never be negative 1. F of 12, for example, 12 is a possible range value for f, so it can be a domain for f inverse. 12 will go in here. 12 squared is 144, minus 5 gives you 139. And if you plug in 139 into here, you would eventually get 12. So the point of those last two slides was to try to defend that the domain of one function must equal the range of the other function. And the range of one function must equal the domain of the other function. So the domain and the range switch. Now we were doing that all along because as soon as you switch x and y, you are switching the domain and the range. As soon as you behave this way, as soon as x and y switch, you are switching the domain and the range between one function and its inverse. So the domain and the range must be switched for two functions to be inverses of each other. And this is how we restrict the domain, allow it to still be a function and have it be an inverse function of something else. And here's what those graphs look like. So the square root function is square root of x plus 5, has a domain of negative 5 to infinity. And the parabola, only half of the parabola is existing here, x squared minus 5. Its domain is from 0 to infinity. But notice, the domain of this red one is 0 to infinity. That is precisely the range of radical x plus 5. And the range of radical x plus 5 is from 0 to infinity. That's the domain of this. And finally, They are symmetrical along the line y equals x. They are completely symmetrical because when you switch x and y, all the ordered pairs switch. So for example, it looks like 11, 4. Now there's 11, 4 again. 11, 4 is an ordered pair on this graph. But then if I switch 11 and 4, I would get 4, 11. And 4, 11 is on the red graph. The only time where it doesn't move positions is precisely when y equals x. Because if y and x are the same, then switching them won't change the ordered pair, which is why it's symmetrical about this line.